Hello and welcome to my talk. This presentation is titled Software-Defined Hardware-Assisted Isolation for Trusted Next-Generation IoT Systems, and is done in the framework of our research in the framework of EU-funded project Avant-Garde regarding automation in manufacturing, and is done at Intelligent System Computer Architecture Lab at Hellenic Mediterranean University in Greece. So let me give an outline of my talk. First, I'm going to talk about a little introduction about industrial IoT revolution in smart industry, and in particular the security challenges regarding IoT technologies and network function virtualization in this context. Next, I'm going to give a little presentation, describe a little bit our solution regarding on-chip protection for network function accelerators in this environment. And next, I'm going to give our evaluation and assessment regarding our implementation of our solution on an FPGA-based prototype. And last but not least, I'm going to provide our summary and conclusions and key takeaway messages from our work. So, IoT technologies, along with other, of course, technologies, cloud technologies, artificial intelligence, software-defined networking, are key factor in what we call today smart industry. From perception and connection layer up to conversion and configuration layer, all these technologies are very important to work together in a smooth and interoperable way in order to achieve optimization of manufacturing processes and flexible management and optimal management regarding industrial processes and maintenance scheduling. So actually the coming of IoT era has brought huge amounts of data moved from end to end, and nodes are collaborating with intelligence. We are using virtualized gateways and network elements with increased requirements for complex functions beyond the abilities of end devices. So in this environment, it's very important to support intelligence and efficient cooperation of devices with in a secure and trusted way. Actually, smart industries and microfactories today, as the setup I'm showing in this slide, endorse increasingly IoT-based automation, but of course with increased complexity at different levels due to multi-purpose software and a lot of different devices that are integrated in these infrastructures, and these are all needed to manage several network protocols in a smooth and secure way, from industrial Ethernet to low power wide area networking. All these devices and software need to work in an efficient way, and most of all in a secure and trusted way. So today the potential of network function virtualization has increased. It essentially includes several different types of applications. For example, in-network controllers of cyber-physical systems can be deployed as virtual network functions to control driverless vehicles. Software-defined networking and network function virtualization work jointly at different layers and in concert with various technologies from architecture level to operating system level. Thus, the attack surface and risk becomes dramatically larger and larger. The focus of our work mainly is at the bottom layer regarding how we can achieve a more efficient network function accelerator in this complex environment. So how we can implement network function virtualization can be done, as I mentioned, in a lot of different layers of course, with different requirements and challenges, but our focus is mainly on integrating network function accelerators and in perhaps a more flexible and an efficient way in tandem with FPGA technologies that are flexible enough to integrate hardware controllers in a power efficient way. So although network function virtualization regarding IoT has been implemented and researched with efficiency, and actually firewalls and intrusion detecting systems are increasingly used in order to guarantee security. Actually, the main focus is mostly interoperability regarding network function virtualization. So what we introduce is a lot more in-depth security regarding these environments, and mostly focus on IoT on IoT infrastructures, and specifically in gateways used in network function virtualization. So how we can realize accelerators for network functions? Actually, technologies today offer a large number of ways to generate and integrate accelerators in system on chips, and in particular with the aid of high-level synthesis tools and FPGA technologies, it's even easier to actually realize network function accelerators. But in this setup and this configuration, the goal to achieve a trusted system on chip with these accelerators, it becomes even larger and larger. So while there are a lot of analysis and research about how we can implement virtualized network functions, and these are actually the focus of deep packet inspection and firewalling implementation in gateways, and mainly at server and cloud environment, with implementing firewalling techniques with anomaly-based inspection and deep packet inspection networks. There's not too much attention paid in how we can achieve lightweight, secure system on chips with these hardware accelerators. So, of course, there are technologies that have developed during the last decades regarding IoT devices and embedded systems, like trust zone and input-output memory management systems to protect processes from malware or faults or attacks in these embedded devices. But as has been researched, like what the slides described, there are a lot of and increasing number of attacks in this environment. So in addition to complex systems that are keep coming up and integrate network function accelerators, it is even more pressing to come with secure solutions in heterogeneous gateways and embedded devices that integrate such accelerators. So let me give the key concepts and the key ideas from our implementation in order to achieve isolation between different accelerators when access the physical memory of the device. What we have actually what we actually propose is a lightweight software-defined interconnect, which actually achieves physical isolation of the memory space that are allocated in each accelerator. This memory space can be either in on-chip SRAM as a separate scratchpad memory, or different areas in a shared DDR system memory. So we can define and actually isolate the memory partitions that can be assigned to each accelerator, either in one-time programmable way or dynamically. This software-defined interconnect is register-based. In the current implementation, we support 16 discrete regions, either as I show in scratchpad memory or in system memory in DDR. And it is actually supported by a software-defined controller, which can be secured at boot time by providing an isolated software and even more signed software. But in addition, this software controller is responsible to manage a central DMA controller in order to transfer data from system memory to the scratchpad memory. But this system DMA controller is a custom-made in order to support firewalling and protection functionality inside. It does not only support fast memory transfers from one memory region to another, but it also supports firewalling functionality. All these components are quite lightweight and can very easily be integrated in the data path of accelerators. But this is not the only way that we can integrate such solution in a system on chip. In addition, a software-defined interconnect can be also integrated in the control path. For instance, in a setup leveraging our work from integrating different accelerators, different function accelerators with an FPGA environment and a packet processing unit, which is responsible to dispatch tasks to each accelerator. We can also integrate a software-defined interconnect in the control path in order to isolate the control path from a different core to a different accelerator through the general packet processing unit. We have an isolated, a secure context and mapper integrated with the software-defined interconnect in such a way that each general packet dispatching unit cannot be physically accessed either from a different core or from a different application running in a different core, as the system can be programmed and configured at boot time. So in this way, if we actually integrate both solutions, both the software defined interconnect in the control path, but also in the data path, we have a fully protected system on chip when we use such accelerators. Let me give some evaluation of such setup. We have implemented a hardware accelerator regarding encryption and decryption based on AES algorithm on a Zinc 7020 platform. This is actually one of the latest technologies provided by Xilinx, and as we can see, the delay of implementing a DMA transfer of one page, actually 4 kilobyte transfer, is more or less comparable to the latency of performing an AES encoding for 48 bytes. And so the firewalling function is actually negligible, since the firewalling is already integrated with the DMA, and it's actually negligible compared to the latency of computing one AES encoding function in hardware. On top of this, we have combined, as I mentioned, both solutions in such a FPGA platform that integrates a dual-core A9 ARM CPU and application processor. But in this setup, we have integrated different accelerators in the FPGA, and we have integrated both the software-defined interconnect in the control path, where the application dispatches jobs to the hardware accelerators, but also at the data path, where the software-defined interconnect controls the partitions in memory that can be accessed by the accelerators. Actually, this design is IOMMU free, since we don't need an IOMMU for protection. All the protection, both in the control and in the data path, is provided by our solution with the software-defined interconnect. We have an actually very lightweight isolation, and we can access the physical memory from DMA controllers that support inherently a firewalling function internally. So let me give an evaluation of this setup. This setup actually integrates everything I described previously, from a general packet processing unit up to two accelerators. One accelerator performs matrix multiplication, and the other performs Sobel edge detection, and of course we have replaced this with AES encryption, but AES encryption and decryption are much smaller than this accelerator, so it's actually has no effect in the results that I'm going to describe next. So we have integrated, as I mentioned, the software-defined interconnect acceleration, and we compare it to the base accelerators as I presented previously, without the software defined interconnect, in order to evaluate the overhead that is imposed by our solution for lightweight protection. We actually have implemented a stream of dispatching kernels to these accelerators, but we used the smallest number of requirements for this kernel in order to consume as little delay as possible, in order to better evaluate what is the rate that can be supported in such platform, and what is the actually impact and overhead of integrating such software-defined interconnects. So from scaling for a number of threads from 1 to 5, these are threads that reside in the application A9 ARM cores, and we have managed to offload the tasks up to 5,000 and 6,000 packets per second, and as we can see in this graph, the overhead is actually negligible, less than 1%, I can say. So in summary, the software-defined connect manager that we implemented offers actual physical isolation for hardware accelerator units, which are very critical in gateways and in IoT embedded devices that integrate such network function accelerator units. But of course, not only hardware accelerator units, but it's very important to provide to application virtual machines to provide support for lightweight security and trusted execution on chip in order to be implemented in efficient and in secure way in such gateway devices, in such IoT infrastructures. Our solution is very lightweight with negligible overhead, and we actually can provide the same or even better security levels of protection regarding isolation compared to other modern solutions that integrate IOMMUs to achieve the same goals. These FPGAs are actually rapid prototypes, which are a great way to show the network function virtualization value, and actually the ramp-up time for developers is very challenging, but to provide security by design is a very important attribute all the way from cloud to edge devices. So these are actually promising days with great potential for software-defined working technologies for next generation accelerators. And in this trend, it's very important to provide security by design in this complex system on chips. So, thank you for your attention. Any questions are always welcome. You can find more information regarding our work in the website of our laboratory, Intelligent Systems and Computer Architecture Lab. So, thank you for your time. Any question?